Okay, this is where we left last time. And remember that we were looking at is how a compiler will use specific known block structures to implement a specific C type of statements, specifically flow control statements using the branch instructions that are in the ISA, the assembly branch instructions, and how it would translate that to assembly, which is equivalent to translating to machine code as well. So this is an example of a while loop. So here we have a single line while. So going through an array, and it's just going to loop there while the value of the members of the array is equal to some constant k. So we can assume that previously the compiler had made associations of the variable I in register 22 and k in register 24, and the address of the array or that pointer is in register 25. So here we have a couple of labels. So that just from a linker perspective, the value of loop is the program address where this instruction resides. So it is a symbolic address in the program memory space. So all we're doing here is adjusting the value of I and multiplying it times 8, because we know, and we're assuming that we have 64-bit integers, and so we know that even though the index I increments by 1 of each element, each of those elements is 8 bytes, and the address is in bytes, and therefore we need to multiply times 8 to get the exact address of the beginning of that element. So that's what that shifting, so that's a good usage of that logical shift instruction that we saw previously. That shifting in by 3 bits is equivalent to multiplying times 8. That's all we're doing in this instruction, is adjusting the index. Then we're going to get to the actual value. So we're going to add the value of the adjusted index to the beginning of the array, which is in register 25, and we get the actual address of the member of the array in register 10. Then we load it from memory, which is the only thing we can do with memory, is either load or store. So since we have the actual address in register 10, we have a displacement of 0. Okay? We have a displacement of 0. So we load that in register 9, and then we do the subtraction to make the comparison. We're going to subtract that which we load, which is save at the index I, and k, which is in register 24. And we know that if the result is 0, which is going to be in register 11, then we have equality. And if we don't have 0, then we don't have equality and we finish the loop. So that's what we're doing here. We're checking for that condition. If register 11 is not 0, that means we don't have equality and we exit. We branch to exit down here after the loop. If we have equality, that means we have to execute the body of the loop. In this case, the body of the loop is a single statement. Is the incrementing of I. If the body of the loop was numerous statements, the scheme is the same. It's just that instead of a single instruction between the branches here, you will have as many statements as you need. And if you have nested loops, then you will have, and you would repeat the same structure inside that space. So this area here, this one line, is really the body of the loop area, which again, in our case, is only one statement, but it could be many more, and it could include nested loop blocks. So here we're doing the addition. So we're incrementing I here, and we know already that we have to continue the loop, because if x11 was not was 0, meaning that we got to this instruction, that means we have equality, so we go unconditionally to the beginning of the loop, and we start processing the next value of I that we incremented here. So hopefully you can see how this assembly language code executes exactly the design intention of this while loop in C. So with your knowledge of C and what you have learned of the ISA of the ARM that we are studying, you should see how these two do the same thing after it has been compiled from this high-level language code to this one. So let's do an example now with the specific values, okay? Let's do an example with the specific values. Let's say that I, which is in register 22, has the value of 1. K has the value 4000. Now notice that I say 4000. I don't say 4000, because this is not 4000. It's in hex. So that's important to distinguish that, because whenever you have the 0x prefix, that means that you have a hexadecimal value. And then register 25 has the beginning of the array, the address of the beginning of the array, which is 1028. So at 1028, you have essentially the first member of that array, so save of 0, let's say. And then later on, 4000 later, you have that value of K over here, okay? Or somewhere you have it. So let's see what the first instruction does. So remember that I is 1. We multiply in times 8, so that gives us 8. Then we're going to add the contents of register 10, which is 8, plus the value of register 25. Excuse me for a second. So we're adding 8 and the value of register 25, which is 1028, and we get this value. That's where the value of the I member of the array is at. So we're going to load that value into register 9. So now register 9 is going to have the value 4000, which is loaded from this address over here. And we then subtract that value from K, and we get 0. So then, since the value is 0, we are not going to branch. We're going to execute the next instruction, the fall through. And we're going to increment I. And we're going to go back to the beginning. So this is the next iteration of the loop. Now that I is 2, so we will do the same thing. Add that to the beginning of the address. We will get that address. We will get the value at that address, 1068. That's the value. And we do the subtraction. So now the contents of register 11 is not 0. And we exit the loop. So hopefully that gives you a good idea how these things work. Now, the high level idea here is that blocks can be visualized as a sequence of statements. Specifically this, the basic blocks that we're talking about, different loops, if, else, else-if type of structures. So the compiler designers, when they study the ISA, they look at instructions that lend themselves to have a specific schemas for the different blocks. What changes is the body of inside the loop, inside the if clauses, but the structure doesn't change. So they have essentially pre-designed blocks that they use along with the associations that they have made to memory and to registers, and along with whatever else needs to be done to make the body of the loop. They can then convert that high-level language to assembly, and then it is just a lookup exercise to convert the assembly to the eventual binary code that is going to be processed or executed by the processor. Somewhere in there, you can have optimization techniques, which the very few ones can be algorithmic in nature. The very best ones, later on, you can have different levels of optimization in the compiler. The very best ones then really become more heuristic in nature. But just the plain exercise of compilation can be automated, because you can come up with these blocks and then populate them according to the type of block that you're talking about. There are more conditionals operations in this reduced ISA that we're looking at. And for that, condition codes are used that are set from arithmetic instruction with the S suffix. So we have add immediate S, and S, and is immediate S. sub S, and sub immediate S. So the S means that these instructions will set condition codes. And the condition codes, they reside in a special register in the processor that the programmer can read, can query, and see what the condition is. So she will know what the result was as far as the condition was concerned. So here we have 4 conditions that can be set. And again, these are specific bits in that condition register. Sometimes they're called flags as well. And the operations to do masking, like the bitwise logical operation to do masking and extract the value of a specific bit, become very important to look just at a specific bit, let's say in a condition code register. So here we have negative. So that means that the result of the instruction was negative. Any of these instructions. That means that the most significant bit was 1. So we have the result was 0. There was an overflow. So the ALU will have logic and circuitry to detect an overflow condition, which is there's a well-known equation by looking at the last or at the 2 most significant bits of the result to know if you had an overflow. So essentially the exclusive ordering of those 2 bits. If the result is overflow, then you set that bit. If there was a carry as a result, you would set that bit. So again, there is a carry out in the ALU, and if that output is 1, then that condition code gets set. Now, what makes having these condition codes available, not only to be read in a register, but also available to other instructions, is that you can have conditional branching that can look and subtract, set the flag, and then do a conditional branching. So this ISA also has a set of branches on equality, on inequality, you can say on arithmetic or relational comparisons, which are all of this. So you can see how the people making the compiler, they have to be intimately familiar with the ISA so they can make use of these instructions to translate any of the high-level code. So let's look at a conditional example of an if statement. So if A is greater than B, then we're going to increment A. Let's assume that A is in register 22 by previous association of the compiler, and B is in register 23. So we can use a subtraction that sets a condition code to set the condition register. So if we subtract, in this case, B from A, that can set a condition register, and we can have a conditional branch. So branch if less than or equal. So here we're looking for A to be greater than B. So if this is true, if this condition is true, less than or equal, that means this is false. So we're going to exit. But if this is false, that means greater than, and the condition is true. Therefore, we do the increment of A. So the assumption is that you have done something meaningful before using that conditional branching instruction, so it works correctly. So you have to do something to set that condition code. So these are the instructions, the ones that end in S, that do that for us. So how do we do sign versus unsigned comparison? So if we have two numbers, let's say in register 22, all ones, and in register 23, all zeros but the least significant bit, which is 1, if we're talking about signed numbers, then this number is 1, but this is -1. So in this case, the value of register 22 is less than the value of register 23. If we are talking about unsigned numbers, then this value is very high. It's actually this value here. And if it's of course greater than 1. So this is just to illustrate how important it is the type of data that you are declaring, and that's why the declaration and strongly typed languages are so attractive, because you have to know how you want that data to be interpreted by the compiler, mostly, not really so much by the processor. The processor is just ones and zeros, it's hardware, but by the compiler, so it can do the right things to implement your code correctly. Okay, now let's go to the next phase in our discussion and start talking about procedure calling. So we have looked at arithmetic and logic instructions, which can be used to do the bulk of assignments and do a lot of the processing that are inside these blocks, like loops and if statements, and switch statements as well. That is allowed by the flow control instructions. So with the flow control and the arithmetic and logic instructions, we can do a lot. We can do all these structures and the bodies inside of them. And again, there is nothing precluding us from doing the nesting or implementing the nesting of those structures as well. It's just more of the same inside the block or inside the body. What we have not talked about are, if we are looking at C as a model language to try to relate that language down to assembly, what we have not discussed is how we do function calls, which are a very important part of C. So that's what we are going to talk about, procedure calling, next. So the ISA specifies which registers at the very minimum are required to be saved so that the compiler can expect those and the programmer can expect those registers to be saved on a procedure call. And also the ISA specifies which registers are going to be used for parameter passing between procedure calls. This storing of registers between procedure calls, if we need to free up some registers for our new procedure that is being called and not disturb the execution of the procedure that called it, and we can return safely to keep on executing our call, our calling procedure, we have to be able to save registers somewhere. That place, that data structure is going to be the stack, which we mentioned a few lectures ago, and we're going to revisit and discuss it in more detail as we go forward here. So the steps required are, we're going to place the parameters in registers 0 to 7. We're going to transfer control to the procedure that we're calling. We're going to need to acquire storage for that procedure. So if we need registers that are not automatically saved, we need to save them, again, in the stack. We're going to do what the procedure needs to do. We're going to place the result in some register for the calling procedure. So we know that a function can return a value. And then we're going to go back to the place where we were called and then execute the next instruction. By convention in the ISA, the address that we're going to go back to, we save that in register 30. Because now, and we're going to see this later on, the program counter, which is a very special and very important register in any processor implementation, has the address of the instruction that needs to be fetched from memory to be executed. So if I'm going to be executing some other part of the code because we're going to do a procedure call, the program counter is going to change that flow. It's a flow change in the program execution. So I need to know what was the value that the program counter needs to return to after the execution of the procedure call. That address of the program counter is stored in register 30 by convention and by specification in the ISA. We have this instruction, jump and link. That means the link part of that is storing the address of the following instruction in register 30, because that's where we need to return to. So that happens automatically as part of this instruction to start the calling of the procedure. And then this is the procedure label. This is just another label like we saw in the branch instructions, which is a symbolic value for some memory in program memory, some memory location in program memory. That's where the call, that's where the procedure being called starts. And we jump unconditionally to that target address. When we do all that we discussed in the previous slide, we're going to have this instruction. Jump register or branch register to that linked register. So it's going to copy the value that we stored, which is really the next instruction that we need to execute after calling the procedure. The value of register 30 gets copied to the program counter. That's part of the execution of that instruction by the hardware of the processor. Okay? And also this type of instruction can be used for what is called calculated or computed jumps, which are useful for switch statements, because you can have a number of different cases and they can be computed, and we can jump to that register as well. I mean, to that memory location as well. So you have seen how we always go back to some C code and try to illustrate the point of how we do this with translating from C to assembly. So here we have a procedure called leaf example. This procedure returns a long integer, which is a 64-bit integer. And then it takes a 64-bit integer G, a 64-bit integer H, and another one I, and another one J. So it takes, those are the arguments. It computes this expression, so G plus H minus the quantity I plus J, and then that's what it returns. So let's say the arguments are G, G, H, I, and J are in registers 0 through register 3. And we're going to return F in register 19. Okay, so we were going through the assembly language implementation of that leaf example procedure or function. And here we have a label, which is the address of that instruction. That's the beginning. The address in program memory of that instruction, that's the beginning of the procedure. So here we're going to be subtracting. We're going to be subtracting 24 from the stack pointer. I should say, so why 24? Because we're going to be storing 3 integers of 8 bytes each. So we need to make space in the stack by adjusting the stack pointer for 3 8-byte integers. And we're going to be doing that storing subsequently. So we're going to be storing the contents of registers 10, 9, and 19. Then we can use them in our own procedure because we don't know if what was there was relevant for the procedure that called this one. And we will have to make sure that the contents, that the state of the machine is intact and preserved and not disturbed by this procedure. So when it goes back, things can just continue normally. So this is what we're doing here. We're saving the contents of these 3 registers on the stack. And we start by adjusting the top of the stack by 3 integers or 24 bytes. And we store first register 10 with a displacement of 16, then register 9, so that would be, this would be 2 down, 1, and then finally the one where we are at. So this is the value of the stack pointer. This is the top of the stack because we adjusted it here. In this case, the stack is growing down. What we call the top of the stack, I mean, could be, if we visualize that the memory is the memory is increasing in addresses as you go down linearly. If I subtract the value of the stack pointer, I am going up. So I am increasing the top of the stack, and the value of the stack numerically is going down numerically. But the way that people draw memory structures, starting with the lowest address at the top, that's why I'm subtracting. I'm going up, increasing the top of the stack here. Then when I do this push, so when we put something on the stack, we call it a push. When we do this push, I am pushing the value of x10 two 64-bit integers down from the top of the stack. And then this one would be 1 from the top of the stack, and this one would be at the top of the stack because it would be the value of SP. At any rate, I have preserved the values of registers 9, 10, and 19. Then I can use them. I'm going to use them to generate that value of F. Okay? So here we are doing the addition, and remember that the values of the arguments were in these registers 0 through 3. So here we're doing the first addition, the second addition, and then the subtraction of the two expressions. Now I have the value of F in register 19. So I use the 3 registers that I saved. But I was supposed to return the result in register 0. So I'm going to add the contents of register 19 with the register 0 and put the value there. So what this does is just move the contents of 19 to 0 because I'm adding with 0. And now I have the value and the result where it needs to be. And I'm done. So now I'm going to restore the contents of the registers that I use from the stack. So here is register 10, register 9, the same displacements, and register 19. I loaded them from the stack. And now I have to adjust the top of the stack because I freed the last or the top 24 bytes or 3 8-byte integers. So I freed the top 24 bytes. So now I'm going to add and adjust the top of the stack by adding 24, which means that now if the top of the stack was here, after doing this instruction, now after doing this one, the top of the stack is going to be down here at a higher address. So this is a diagram that shows this, okay? But the only thing is that it's drawn upside down. So now here we have the high address at the top and the low address at the bottom. So we're still consistent because we said at the beginning we have the stack pointer over here, and by the time that we have pushed the contents of registers 9, 10, and 19, the top of the stack is pointing to the last thing that we pushed, which, if you recall the code, was the contents of register 19, and that is at a lower address. And after we restore the contents, which is called doing a pop from the stack, now we return to the original value. So when we subtracted 24 from the stack pointer, we made it this value. And then we stored these contents with displacement, with a displacement of 16, with a displacement of 8, and with a displacement of 0. Then we did the same thing. We stored them in the same manner with the same value of the stack pointer, and then we added 24 to that value of the stack pointer, which puts us at the same value that we were before. Now this is where the top of the stack is. It can be used by something else. This is very useful if you have nested procedure calling, and we're going to see that shortly. So again, the ISA specifies and recommends registers that are supposed to be saved and registers that you're not guaranteed to have saved. So registers 19 through 28 are saved registers, and registers 9 through 17 are what is called temporary registers. And again, the stack is a nice data structure because it lends itself to nested procedure calling, and you can keep on storing anything that you need by pushing on the stack, and then you can restore by popping. So it is a last in, first out type of data structure that lends itself to recursive, not just recursive, but nested procedure calling, saving of data. All right, so let's keep going. And this is something that we mentioned before, which is how different sections of what we store in memory are reside together in memory, and the operating system manages the different sections of memory. But it's really a logical partition that the operating system keeps. One of the important parts that we want to bring up is, for historical reasons, the text area is where the programs are. Then you have static data. Then you have dynamic data. And the stack is on top of that. The stack grows down numerically. And whatever is here is dynamic data, which is called the heap. So this is where you can allocate memory by using functions like malloc in C, or operators like new in C++ and Java. When you get a stack overrun, it's when you intend to grow the stack and you encroach in dynamic data or heap memory space that has been allocated. The operating system watches that and you get a stack overrun. Now let's take a look at how we encode data in memory. So, and it'll be a nice transition as we go into the arithmetic chapter later on. So we can encode data as bytes. So a lot of the ASCII codes are 7 bits. And then the extended ASCII use all 8 bits, still bytes. And then we have Unicode. So this is actually characters that are encoded in 32 bits. So there they use Java and C++ wide character data types, and that also allows to encode symbols and different languages and alphabets. Not languages, but alphabets. Then we also have UTF-8 and UTF-16, which is variable length encodings. And that's useful to maximize bandwidth during the transmission. These things are very useful in the web type of communications in the HTTP protocol. So you can see that data has different lengths. And that's why we can address the memory a byte at a time, because many times we don't need 64 bits, which is 8 bytes. It would be a waste of bandwidth and memory space to store a character, a plain character, as a 64-bit piece of data. We'd be wasting 7 bytes or using 8 times as much as we need to. But we need to be able to get to that data that is stored in fewer bytes than the width of the data path of the processor. So we have some other nice instructions in the instruction set. We can have load unsigned register with a byte. And we can have a store doing the same thing. Actually, this is not unsigned. I'm sorry. Then we can load the half word. And remember, if our word, which is the definition of the width of our data path, is 64 bits, half word is 32 bits. So we can get to all those subfields or subparts of a word, both with loads and stores. The instruction works out the same way. So the load uses an offset, an immediate offset, and the contents of a register, and puts the result in a destination. And the store stores just a part of a register. Remember that the registers are 64 bits. Just stores that part of the register and uses the address, the base address from another register, and an immediate offset. This is the same idea here. So that makes, again, that's part of the arsenal, that's part of the instruction set. And we're going in a lot of detail through different instructions, a few at a time, because what you need to be thinking and what we're going to be doing in chapter 4, which is longer than this chapter, is now how do we design the processor to support all these instructions? That's what we need to be thinking about. And it's good to have an idea of the level of complexity that we are signing up for when, as architects, we come up with an instruction set. Because now we have to deliver that in the form of hardware. Let's do another example of, and this is just to illustrate the byte type of operations, because here we have a string copy function, which is going to copy from this source string to this destination string. And here the arguments are 2 pointers for the arrays where the strings are. So here we have essentially in C, size t is the size of a byte. So, or an integer. So here we have declare the value of I. We start at 0. And we're going to copy y to x until we hit a null, which is the value of 0. That is a null string, which is, a null character, which is used to denote the end of a string. So we're going to copy y to x until we reach the end of y, which is the source string. And then we increment I, and we're incrementing I in the loop here. This is the body of the loop. All right, let's see how we do that in assembly. So here's the beginning of our procedure. We're going to make a space for one register at the top of the stack. So by now you should be familiar with this couple of operations, which is here we are adjusting the top of the stack. Here we are pushing the value of register 19 on the stack because we're going to use it as our I variable. So here we are zeroing out. So this is the initialization of I equals 0. Now we're going to put the value of the beginning of y in register 10. And then we're going to load the first character of the source string. We're going to do the same thing by loading register 12 with the beginning of the destination string, x. And then we're going to store at that address the contents of register 11, which is the actual character of the source string here, y. At that point, we have copied a character from y to x. And now we test if that character was null. Remember that the null is actually part of the string. It needs to go there. So before we stop doing this, I need to make sure that the null from y went into x. So that's what we do the comparison here. We do the comparison by testing the value of x11, the last character from y that we put into x. If it's 0, then we go to L2 here. And all we're doing here is restoring register 19 that we were using for our index I by doing a pop, adjusting the top of the stack, and then exiting with the branch and from the link register. Here we're doing the return. If we are not done, if the character is not null, then we go back. Okay? And then we're going to adjust the address. We're going to adjust the address and get the next character from y. Adjust the address of x, store in x, and again test the string. And if it's not 0, we do it again. And then when it's 0, we exit. So the mechanics should be well understood by you now. The only thing is that we are using the byte type of instructions because we're dealing with characters. So those instructions are very useful.